Can you hear me now? Good. It's a pleasure to be here, not only scientifically. I'm really glad to see all the friends that I've missed for some time, old and new. And yeah, I basically last year in Continuous Advances, I gave a talk but with a similar title, except it was in 3 dimensions. I'm going to talk about 4 dimensions now, and I'm going to correct some things in 3 dimensions. So basically, you know, it will give some hints about what phase in 3 dimension is. The talk is with these 2 gentlemen. Nakarin is a postdoc at Durham, and Mohammed is another faculty. Well, this is, I wanted to comment, you know, if you're going to collaborate with me, you better make sure that the Google results returns good pictures of you, because I take the first ones. So, yeah, so let me plunge into it and immediately review what kind of prerequisites of this thing. What I'm going to consider is SUN Young-Mills theory coupled to both adjoint and fundamental matter. But my starting point will be the super Young-Mills theory, which just has adjoint one while flavor of adjoint matter. And I'm going to keep only one while flavor, not going to. In fact, for the purpose of this talk, I'm only going to add one fundamental just to make it simple. Most of the interesting things that I want to discuss happen here. But first, let's review the one adjoint while fermion. This theory is supersymmetric, and it's known to have well, it has two important symmetries. One is the discrete chiral symmetry, which rotates the phase of the while fermion. And the other one is because this is adjoint representation, there's a one-form symmetry under which fundamental Wilson loops transform as a phase. The phase of this theory breaks the discrete chiral symmetry spontaneously by the development of the condensate, much like in QCD, except the chiral symmetry here is discrete. And because it's discrete, it has n vacua, which can be labeled by this integer here, by this phase here, which is nth root of unity. So since vacua are discrete, we can take 2 vacua, vacuum labeled by k and vacuum labeled by k prime, and they must be separated by some kind of a domain wall, which you can label with n, which is the difference between these two integers. Now, this domain wall was conjectured to be dual to super Young-Mills theory in 3D with some Chern-Simons level related to this n here, and by these gentlemen here. And that theory was analyzed. That theory and related theories were analyzed by Zohar and his collaborators, and conjectured to be a TQFT in a TQFT phase of this type. So my interest, actually, this is the connection with the last year's talk in 3D, is that we're going to modify the theory in the bulk and also make this assumption that there's a relation to some theories of the kind in 3D and see what 3D phases exist. But of course, that was my original interest of looking at 4D, but we will also have to understand the phase diagram of the theory in the bulk. So now what we're going to do is we're going to take this super Young-Mills theory and we're going to add massive fundamental matter, which is not going to be a supersymmetric multiplet. So we're going to break supersymmetry explicitly. We're going to add massive either one flavor of fermion or boson. But again, for the purpose of this talk, I'm going to just focus on the fermion. The boson has also an interesting story, but I won't have time for it. So the question I want to ask is what happens as mass m is reduced? And in particular, what happens in the bulk and what happens on the domain walls? When mass is very large, of course, nothing will happen. You can just integrate out massive matter. But when you reach the scale of lambda QCD, then something could happen. And this is what I want to understand. And I'm going to make a connection with 3D here by assuming, as you will see, there's still going to be some domain walls. And in particular, you know, when domain walls are, when mass is very large, the theory in the bulk has some massive fundamental matter. And it was conjectured to be super Young-Mills with some particular Chern-Simons level. And yeah, sure, but I'm looking at low energy dynamics. I'm looking whether there's a phase transition. Okay. You mean on the domain wall, or? That's correct. There's going to be actually some change on the domain wall immediately. There's the domain walls actually spontaneously break supersymmetry, and there's a Goldstino on the domain wall, which I expect to be lifted immediately. But yeah, the TQ of T though should be robust, right? You cannot just lift it immediately. But you're right, yes. So I'm going to conjecture that the theory on the domain wall, at least for very massive matter, is again super Young-Mills in 3D with some fundamentals added to it. And that was exactly the theory I was talking about last year, if you happen to. Yes. Well, no. Well, that will be changed somehow in the in the theory. With fundamental matter. Well, I mean, it depends on how you probably want to match so that when you integrate them out, the level is that of but yeah. Mostly I will focus on T preserving domain wall, because the talk of last year, if you remember, was about T preserving 3D theories. So I will pick the level so that it's T. Well, if you remember, I don't know, you probably don't remember. Yes. Yes. There was also a conjecture of it's closely related. That's right. These are more modern, refined conjectures. Let's say. Okay. So what are the symmetries? And the symmetries. So as I said, the theory is either supplemented with a boson or a fermion. I'm going to focus on this case. And the symmetries now, there's no one-form symmetry because I broke it explicitly with the fundamental matter. But instead, there's a baryon symmetry, which rotates the phase of either the fermion or the boson. And notice that the way I normalize this, I normalized it with the parameter alpha, so that alpha is 2 pi periodic up to gauge transformation. Because when alpha is 2 pi, this is a pure Zn phase, and that's a gauge transformation. That's not a global transformation. This turns out to be important. And in fact, a consequence of this is that there will be a mixed anomaly between U1 baryon and Z2n chiral. Yeah. Well, when this is pi, this is not a fermion number. it would have to be something like n times pi for that to be the case. But
no, of course. No, but I mean, you said that returning back after 2 pi there, and I'm trying to say that returning back after pi there.
After pi n, it's still a global symmetry, but cannot be spontaneously. Well, it could be a global symmetry or not, depending on whether n is even or odd. But yeah. Of course, yeah. There are two kinds of theories. But now the way I'm going to approach this is actually to go to the massless limit, because there's actually more symmetries in that case. In that case, there is a non-anomalous U1 chiral, which rotates the phase of the fundamental and of the fundamental and of the adjoint in such a way that there is no anomaly. Okay, you can cancel the contribution, the anomalous contributions of the two fermions, and form a U1 chiral symmetry, which is exact now quantum mechanically. And in fact, there's a whole bunch of triangle anomalies here. There's a pure chiral anomaly, U1 chiral anomaly with this coefficient here. This coefficient you just get from sum of the cubes of the charges of the adjoints and of the fundamentals. There's n squared minus 1 adjoint and n fundamentals. There is a mixed U1 chiral, U1 baryon, and it was crucial to get these are baryon gauge fields, which have to be properly quantized, and it was crucial to take into account that this alpha parameter was defined as I defined it, that it changes up to a Z2 phase. It will actually, putting these baryon fluxes will give you kind of a fractional color fluxes. There's going to be intertwining in the two. But if you do everything correctly, you get this. And then there's a mixed gravitational anomaly. This is the first Pontryagin class of the tangent bundle. There's a mixed gravitational anomaly with the chiral symmetry. Yes, exactly. So under discrete chiral symmetry, this is just, if you put alpha to be 2 pi over n, this just does not transform at all. Only this transforms. So it's a subgroup of the U1 chiral. Yeah, in the boson case, it won't be the case, but something else. Actually, if you condense the boson, let me just say this. If you condense the bosons completely, you get the fermionic theory. You Higgs one part of the gauge group, and you get a one fundamental fermion, and so you reduce it to this case. So it's can be reduced. Now, when you actually add a mass and you break this U1 chiral symmetry down to Z2n chiral, all of these anomalies actually remain. None of them, something remains, okay? This one was studied in a paper by, I don't know how to pronounce this. Can somebody help me? In 2018, but also by Zohar with his usual suspects, some of the usual suspects, that even though you break the U1 chiral symmetry down, something remains. These two terms are related to some, if you wish to think of it as a Zn cubed triangle anomaly, but also this anomaly remains. And you can see it kind of by reducing this thing to a Zn gauge field. You can still not remove it. This is like a 5-dimensional inflow action, and you can see it in more detail. But the point is that all of these anomalies still remain even when you add this. Yes, this person did that. Yeah, it's the same. It's the same. I think it's the same. Yeah. So you can rigorously show this, or no, I can't, but there are people who can, who claim that they can, and I believe them. My point is that all of these anomalies are still there in some shape or form. And therefore, the most natural, you see, all of them involve the chiral symmetry. And therefore, the most natural way to saturate all of them is just to break spontaneously chiral symmetry. In fact, this is a chiral symmetry and gravitational anomaly, so you can't really saturate. You could I'll consider one more case where you can saturate, how you can saturate them. But the most natural way to saturate them is just to break this discrete chiral symmetry throughout. And at the end, when mass is exactly 0, you just have a U1 symmetry, which is spontaneously broken down to Z2. So you have an exactly massless Goldstone boson here. However, there is an a priori alternative, and the alternative is with composite fermions at this massless point. And there is a choice of charges for these composites, which will do the trick. Okay, I here just outlined the choice actually relies on the fact that the cubes of these charges of the would-be composite fermions of the chiral charges has to have this this index here, exactly like here. It has to add up to this thing, and then you note the identity that this thing actually gives you the sum of i's from 1 to n gives you the most important piece, and then you just need one more charge, which is the Q0 charge, which is -1. It's given here. So the rest of the charges are just -2i plus 1. And then you have to assign baryon charges to satisfy this, which means only 2 of these fermions have baryon charges which are opposite, and then everything is satisfied, the gravitational anomaly and everything is satisfied. So this is one potential a priori option. But that option is actually excluded by a type of Vafa-Witten theorem considered by Weingarten around the same time, where he proved in QCD, but the proof goes throughout. It only uses actually correlators of fundamental fermions and positive definiteness of the measure to prove that any baryon is heavier than a meson. And so if a baryon is massless, then a meson should be massless, but the only way a scalar should be massless naturally is if it's a Goldstone boson. So a massless baryon would imply a Goldstone boson, but then it kind of is not naturally. Yes. Adjoint is always massless. Yes. Yes, we checked it. Yeah, we checked it. Yeah. Yeah. It is positive. You mean on the lattice? On the lattice, you have all kinds. So, for example, actually, in Weingarten considered the theory on the lattice, and on the lattice he couldn't prove this identity. He had to prove a slightly weaker identity because the Wilson Dirac operator did not have this positive definiteness always. So he had to assume that there's a certain number of flavors and so on. But in the continuum, at least as a formal proof, this works. And the Pfaffian of the wild fermions. We were very confused. Actually, I learned about this from David Tong, and he said it for a very similar theory. And I asked him, "Are you sure this is positive definite?" And then me and Nakarin sat down and worked it out. No, on the lattice, yes. In the continuum, it's a formal proof. In the continuum, you can define this as positive definite. Yes. You can get away from the sign. Okay. So, yeah. In the continuum, certainly the sign is not, at least formally. Now, if you regulate it with polyvirars or something like that. So this is excluded. And U1 chiral symmetry is naturally just spontaneously broken. So this is the phase. But there's still a question of how it saturates all the anomalies. Because if you just consider a Goldstone boson in the infrared, it doesn't really saturate formally anomalies. And this bothered us for some time. And then when we realized that there are these fermions which saturates anomalies, we just realized we can gap them out in a symmetric way just by coupling to the Goldstone boson. So they're massive, but you know, I like to keep them in just because you saturate the anomaly. But their true purpose is that they will actually show up as massless on vortices in this Goldstone boson phase. So this mass term is not well defined at the vortex, and it kind of vanishes at the vortex, and this is where you will see the fermions. But so this here, yes, so these two are charged under the chiral symmetry, right? So the mass term without the Goldstone boson, you cannot write this mass term because it's charged under chiral symmetry. But now you have a light degrees of freedom, the Goldstone boson, which can soak up the transformation of this mass term. And so it's a well-defined mass term which gaps out your fermions, and these fermions saturate all the anomalies. So you can't write the Wessel-Minowitten term. That's the problem. For a U1, how do you write the Wessel-Minowitten term? It's just a U1 Goldstone boson. All of them. So phi f wedge, well, yeah, but that's when you gauge it. But when you put background fields, yes, that's the anomaly. Okay, maybe you're fine with that, but I wanted to see what degrees of freedom are there. In fact, one of my biggest concerns was I'm going to look at domain walls here, and I was worried that maybe domain walls have some degrees of freedom on them. Yeah. Yeah. That's going to reproduce it, right? But these fermions should match that anomaly by construction. Yes. Now these are the meson. What I mean by meson are insertions of fundamental. This is what what Weingarten proved was only for fundamental matter. So what he considered a meson were just insertions of fundamental fields. And the point is that if you have a baryon, which is carries n insertions of fundamental field, you can show that it has a larger mass than a meson, which is just two insertions of the fundamental. Yes. How am I doing on time? Okay, here I inserted now what I want to do is I want to go to the massive limit in this effective theory. The effective theory I wrote down has a massless Goldstone boson, but and U1 symmetry, which is spontaneously broken. I now want to break it explicitly down to Zn by inserting some mass term for the fundamental Dirac, which is something like this plus its complex conjugate, and that is proportional to this operator in the effective theory. And as you see, it induces a cosine n phi term, which leaves n degenerate vacua. And for completeness, I'm also going to insert a mass of the adjoint, and the mass of the adjoint would couple like this. It's the adjoint's modulus is related to the theta angle. You can put all the theta angle dependence. Now the theta angle becomes physical because both fermions are gapped, and the theta angle can be put in the phase, and it generates this cosine phi plus theta over n term. And generically, for generic value of theta, only one true vacuum remains. But if you dial theta to some particular value, and if the masses if the mass of the adjoint is sufficiently large in its modulus and theta is equal to pi, then you will have two degenerate vacuum, just like in pure Young-Mills theory at theta equal pi. So, oh, sorry, this was, so the phase diagram looks something like this. If you plot the phase diagram as a mass and mass of the adjoint to the power of n, so that this is the theta equal pi, basically, when this object is negative, this is theta equal pi. Then you have this phase diagram where Zn chiral is spontaneously broken to Z2 here, and there are n vacua. If you go upwards with mass of the adjoints, then you just trivially gap over, you have just one vacuum. But if you go down and mass of the fundamentals is sufficiently large, you are in the T broken phase, you have two degenerate vacua. Two of these vacua still remain. And at the end, there's a massless pseudoscalar, which Zohar contributed to this. This is the QCD, basically, at theta equal pi with one flavor. Well, one fundamental favor, and they already pointed out that there's this massless pseudoscalar, which actually becomes this massless Goldstone boson at when adjoint fermions are massless. So, are there any questions about the bulk? Oh, in plotting, we weren't careful about the shape, but yes, you can. You can in principle, but because this is m to the n, it would be okay. So we didn't bother. It's linear, I think, in m adjoint. If this was m root of this thing, then this would be a line. So are there any questions at this point before I continue to the domain wall? No. Yeah. Okay. Not the question. Timestamp. Okay, so now I want to go back to the massless adjoint case and ask about what are the domain walls. And now the domain walls in this theory are actually kinks, okay, which interpolate from, for example, phi equal to 0 to phi 2 pi over n. And what do we know about them in this small mass, fundamental mass regime? Well, they do not carry any fermion zero modes. You know, when we put these massive fermion zero modes, a priori, I thought maybe this is why I worried about these anomalies. I thought maybe, although there's no anomaly reason for domain walls to carry them, at least not all of them, some of them may, none of them carry any fermion zero modes, and therefore they're trivially gapped. This is unlike the large mass where there was a TQFT. So that already indicates there's a phase transition. The domain walls also, the domain wall, for example, from here to here, repels from the domain wall from here to here. So the composite domain wall from here to here is actually unstable. They repel, it decays. This is again unlike in super Young-Mills where there are composite domain walls. So there must be a phase transition. So that's statement number one. This 3D theory should have a phase transition. Okay. And the phase diagram, actually refined phase diagram, looks like this. Even though there's no transition in the bulk, there is still a phase transition on the domain wall where TQFT gets eradicated in most cases. But there's one domain wall which is special, which actually does have anomaly inflow and cannot be made trivial. And that's the domain wall which goes from here to here. Now, I already said that such domain walls are not stable, but they should correspond to, they're stable actually in super Young-Mills. And they are T-preserving because T-symmetry, you can think of T-symmetry as flipping this to this. So the T-symmetry is preserved if I go from this vacuum to this vacuum. And if it really bothers you that in my effective theory this is not stable, I can always add some Zn, Z2n breaking deformation down to Z4 so that I only stabilize these two vacua. Okay, that's always something I can do. And I'm going to make a claim that this is somehow related to the 3D theory, which are T-preserving. And these cannot be trivial. And indeed, they are not trivial, because if you lift these vacua here now, the only way, just with a small deformation, the only way you can go from here to here is either going this way or going this way, which means there are two states. And it means that the domain wall theory breaks spontaneously T symmetry. There is actually a mixed TU1 baryon anomaly inflow on this domain wall, and this is consistent with that. And last year, if you remember, I was mostly trying to saturate, if those who were looking at my talk last year, I was mostly trying to saturate this anomaly by massless composites on the domain wall. But it turns out that T symmetry, and I said you can also saturate it by breaking T symmetry, but then my talk would have been over way faster. So you could, but that's not what happens here. Maybe you could. I mean, in principle, it's matched by TQFT when fermions are very large. And we were conjecturing that that TQFT gets destroyed. No, but there's T-preserving TQFTs. But let me just, in the last minutes, also make a kind of a stretch of the imagination conjecture that perhaps there may be two phase transitions on some domain walls, especially for low n. And the reason why I think that may be possible is that this is the massless case, and there's a kind of Mexican hat. When you add this deformation, these are shallow vacua, and that's why you have T-symmetry breaking. You're kind of surfing along this valley. But if you take the mass of the order of lambda, if you stretch this picture, then there's just one scale. And in the origin of this potential for some condensing scalar, order parameter of your spontaneous breaking, there may still be some trajectory which takes you through the origin where there should be massless fermions. So it's not inconceivable, especially in SU2 case, where for a one scale potential, this is kind of pair of pants is the most natural potential, that you go through the origin and you have free fermions. So three phases are not completely excluded, but most likely for sufficiently large n, you just have two phases on the domain. Yeah. So I think for SU2, probably there may be an intermediate phase. But you see, for SU2, when mass is very small, this is Mexican hat with two minima here. So you still don't have a one scale potential, but maybe in some intermediate regime, you do have going through the origin where there would be fermions. Okay, so my conclusion is more or less what I said so far. So these anomalies seem to completely constrain the bulk phase diagram. The Weingarten Waffa-Witten theorems exclude massless composites in the bulk. Z2n chiral symmetry is naturally spontaneously broken, just like in super young mills, but still there is some transition. This is a different phase. It has a different kind of domain wall in some sense, not in terms of low energy bulk excitations, but domain walls have different excitations. Now, T-preserving domain walls break T-symmetry spontaneously, and I think this is good evidence to indicate that QCD3 with this matter content also has a transition in TQFT, turns into T-broken phase, at least for small enough mass. But there's a possibility of intermediate composite domain wall phase, especially for SU2. And there's a generalization for multi-flavors, but most of the essential ingredients are. So with that, I'd like to thank you for listening.
Well,
there is no fermions of the fundamental domain modes, but the fundamental vortex are still not fermions.
Yes. Yes, because of this potential, right? I mean, if you look at this potential and you take a vortex, somewhere in the middle of the vortex, you have to you go through the origin. So the origin. Yes. Yes. Yeah, the wrong anomaly. Right? Yes. Yes. Yeah. So this is exactly. So you can think of these fermions as candidates for the vortex. Fermions, yes. Yes. Right. Yes, that's a very good question. So the difference there is that when mass goes to zero, then there's a runaway potential for one flame. Yeah. Small mass, yes. But it's a very good question. I have not studied that in detail. Is it? Mm-hmm. I see.
In without impact. So you know, in detail there. I mean, you stop run away and
right.
Yeah, and you know,
they were able to study for all values of mass, including intermediate.
Right.
And they did indeed find a 3D theory with multiple things.
Okay. Very good. Yeah.
So either break for symmetry a little bit.
Very good. Yeah. Thank you. That was Benini, you said?
28.
Well, I think it's an IR duality kind of. It has the same anomalies, the same. Yeah. It's an IR duality. If you wish, it's effectively theta angle pi. Oh, it's the same. You can rotate the phase into one or the other. This is by using a non-anomalous chiral symmetry rotation. Remember, there's a non-anomalous chiral symmetry rotation when masses are zero, which turns into just shuffling the phase for the. So the T preserving domain wall is only for n even. That's correct. Yes, but for the bulk phase is the same. So there's no anomaly inflow on any of the domain walls when n is odd. So they're all probably trivial. I mean, they're trivial for small mass, but maybe for, I don't know what happens intermediate. There's a TQFT on them until lambda QCD.
No questions.
Maybe I should say one more thing about T preserving TQFT. This is what we studied. There's a Goldstino there, and interestingly enough, on it cannot be lifted because there's a pure T anomaly which protects it. So it will get lifted only when TQFT is destroyed because the three conspire to match the anomaly, which Zohar and company discovered. But even when you add fundamental matter, you cannot lift it, even though you broke supersymmetry, which is kind of interesting because. Excellent, yeah.